Welcome to the deep dive. Today, we are immersing ourselves in a piece of research that really did just fundamentally redefine modern machine learning. We're talking about the 2017 paper, Attention is All You Need.
And for anyone whose background is, rooted in sequence modeling, and since you're probably familiar with the history of recurrent neural networks, LSTMs, this paper is basically the moment the entire field of NLP just hit the reset button.
Absolutely. I mean, before 2017, if you were doing anything with sequence transduction, like machine translation, the path was pretty clear.
It was standardized, yeah.
You had these complex decoder architectures built on stacked LSTMs or GRUs, and maybe you had an attention mechanism bolted on top to kind of manage the state. That was it. That was the peak.
Right. So our mission today is to really unpack not just the mechanics of the transformer architecture they introduced, but the core engineering constraint that Vaswani and his team were trying to solve.
And their solution was, well, it was radical.
It was just dispensing with recurrence and convolutions entirely. They bet everything on attention.
And the results were not subtle. This wasn't some, small iterative improvement. The base transformer model hit a new state-of-the-art BLEU score of 28.4 on that standard WMT 2014 English to German task.
And to put that number in perspective for you, that single model beat the existing best results, which were often these complex ensembles of the very best recurrent models, by more than 2 full BLE warm points.
Which is huge.
It's massive.
Yeah.
But the real structural change, the thing that made everyone's jaw drop, was the speed. The large transformer was trained in just 3.5 days on 8 GPUs.
That's nothing.
It completely slashed training time compared to what came before, getting better performance at a fraction of the computational cost. I mean, that's the real magic of this paper.
Okay, so let's start right there with that computational cost, because that really is the foundation for this whole architectural pivot. If LSTMs were so good, so dominant for sequence data, what was the flaw? What was this bottleneck?
The fundamental problem is, in a word, parallelization. A recurrent model, just by definition, has to process things sequentially.
One after the other.
Exactly. To calculate the hidden state at position t, let's say, you absolutely have to use the hidden state from the previous position, t-1, plus the new input. There's no way around it.
So if you've got a sentence with 500 words, you can't even start thinking about word 500 until you're done with word 499.
Precisely. And that means for any single training example, the computation is inherently serialized. Now, of course, you can batch sequences together.
Right, for training efficiency.
But the time it takes is always dictated by the longest sequence in your batch. And as data sets got bigger and people wanted to use longer sequences, this dependency just became this massive limiting factor on both speed and scale.
And this problem wasn't a secret, right? People were trying to solve this.
Oh, absolutely. There are other approaches, mainly using convolutions. You had things like Facebook AI's ConvS2S or DeepMind's ByteNet.
So why weren't those the answer? They were parallel, weren't they?
They were, and that's a key point. They did solve the parallelization issue, because convolutions can compute representations for all input positions at the same time. But they ran into a different scaling problem.
Which was?
Path length.
Yeah.
The dependency path length.
Okay, break that down. For someone listening who knows sequence modeling, why is path length so important?
Think about it this way. You need to relate the very first word of a sentence to the very last one.
Yeah.
This is crucial for long-range dependencies, right? Like subject-verb agreement or figuring out what a pronoun refers to.
Sure.
In an RNN, that signal, that dependency, has to travel through every single time step in between. So its path length is proportional to the sequence length, what we call ON.
And for the convolutional models?
A bit better. For something like ConvS2S, it's still linear, ON, unless you stack a ton of layers. ByteNet was smarter. It used dilated convolutions to get it down to a logarithmic path length, O log n.
Okay, O log n is a big improvement over ON.
It is, but it still means that as your sequence gets longer, the number of steps required to connect the two ends still grows.
So this is the truly radical insight of the transformer. Realizing that self-attention lets the model relate any two positions, no matter how far apart they are.
With a constant number of operations.
A constant number, the path length becomes O1.
And that O1 complexity is the entire game changer. It means you can massively parallelize training, which makes it orders of magnitude faster, and at the same time, those tricky long-range dependencies become trivially easy for the model to learn.
Which makes that core mechanism, the attention itself, absolutely critical to understand. Let's move to that building block, scaled dot product attention.
Right. So at a high level, an attention function just maps a query, a set of key value pairs, K and V, to an output.
And the output is just a weighted sum of the values, the V's.
Exactly. The weights tell you how much attention to pay to each value, and they're calculated based on how well the query matches the corresponding key.
Okay, so the transformer uses a specific type, scaled dot product attention. Let's walk through the formula, because that scaling factor is, well, it's brilliant.
So the formula is softmax of Q times K transpose divided by the square root of dk, all of that multiplied by V.
Let's unpack that. The QK transpose part, that's just a dot product.
That's right. A big matrix multiplication that calculates a raw score for how much every query aligns with every key. Super efficient on a GPU. Then comes the clever part, dividing by the square root of dk.
And from a purely practical implementation view, why is that scaling factor, the square root of the key dimension, dk, so essential for keeping things stable?
Because when that dimension dk gets large, say 64 or 128, the dot products themselves can just grow huge in magnitude, really, really big numbers.
And if you feed huge numbers into a softmax function,
You push it into regions where the output is basically just 0 or 1, and the space in between is incredibly steep.
which sound like a perfect recipe for vanishing gradients.
Exactly. The gradients become infinitesimally small, the network just stops learning, and your training becomes unstable. Scaling by 1 over the square root of dk just pulls those values back. It keeps the softmax in a healthier region where the gradients are nice and stable. It allows for fast convergence.
It's such a simple, elegant piece of engineering right inside the core function. I also remember the paper noting they chose dot product attention specifically because it was faster and more memory efficient than the additive attention that was common back then.
That just underscores the whole point of the paper, speed and scale. They tailored the math to fit the hardware.
Okay, so moving from that core mechanism, let's zoom out to the architecture. It keeps that classic encoder-decoder structure, but the layers are built from just attention and feed-forward networks. Walk us through the stacks.
So you have both an encoder and a decoder, and each one is a stack of n equals 6 identical layers. And the key is that every layer, every sublayer, produces outputs of the same fixed dimension D model, which is 512 in the base model.
Let's start with the encoder stack. 2 main sublayers. But more importantly, how did they keep the signal from degrading through 6 full layers of this stuff? Residual connections and layer norm must have been crucial.
Oh, absolutely critical. Each encoder layer has a multi-head self-attention sublayer and then a position-wise feed-forward network. And around both of those, they wrap a residual connection and then immediately apply layer normalization.
So it's layer norm of X plus the output of the sublayer.
Exactly.
Oh,
That
cool.
structure is what prevents the gradients from vanishing and allows information to flow so deep. Without that, training a deep stack of attention layers would probably just fail.
Now, the decoder is similar, but it has a much tougher job, right? It has to be autoregressive. It can't cheat and look at the future. So what are its 3 sublayers?
It starts with the same 2 from the encoder, a multi-head self-attention and a feed-forward network. But the crucial addition is a 3rd sublayer sandwiched in between them, the encoder-decoder attention.
And what's the role of that one?
That's the bridge. In that layer, the queries come from the decoder itself, from the previous layer. But the keys and the values come from the final output of the entire encoder stack.
So it lets the decoder look back at the whole input sentence while it's generating the output.
Precisely. It can dynamically focus on the most relevant parts of the source information for whatever word it's trying to predict next.
And that constraint on the decoder's own self-attention, the masking, that's how it avoids cheating.
Yes. The decoder's first self-attention layer is masked. All it means is that when the model is calculating the output for position I, it is physically prevented from attending to any positions after I. It preserves that autoregressive property. You can't peek ahead at the answers.
Before we hit multi-head, can we just touch on that second component in every layer? The position-wise feed-forward network. It seems so simple. 2 linear layers with a real U, but it's a huge part of the model's capacity.
It is. It's where a lot of the sort of heavy lifting happens. It provides the nonlinearity that attention on its own doesn't have, and it's applied independently and identically at every single position.
Like a 1-by-1 convolution.
Very similar, yes. And that interlayer dimensionality, DFF, is massive. It's 2048, even though the input and output are only 512. That huge internal capacity gives the network the power it needs to really process the rich representations that the attention layer creates.
Okay, now for the idea that gives this architecture its real power, multi-head attention, why not just have one big 512-dimension attention mechanism? Why split the Q, K, and V vectors into 8 different heads?
That is a great question. If you only use one large attention head, You're essentially forcing the model to compute a single blended weighted average of everything.
Which might average out important detail.
It could, yeah. It might blur distinct pieces of information. A single head could struggle to pay attention to, say, syntactic structure and long-range semantic meaning at the same time.
So MHA is the solution.
It is. They linearly project the Q, K, and V vectors H times 8 times in the base model, and each of those projections goes to a separate attention head. Each head operates on a smaller dimension, just 64. Then the outputs of all 8 heads are just concatenated together and pass through one final linear layer.
And what's the practical benefit of having these 8 parallel focus mechanisms?
It lets the model jointly attend to information from different representation subspaces at different positions all at the same time.
So one head might be looking at grammar.
Exactly. One head might specialize in syntax, linking a verb to its subject. Another might be all about semantics, linking a pronoun to something that was said 30 words ago. By running them in parallel, the model gets this rich, multifaceted view of the input. It completely avoids that averaging problem.
Okay, so we've thrown out all sequential computation, which is great for speed, but it means we have no built-in way to know the order of the words. How does the transformer inject that sequence order back in?
Right, because self-attention is a set operation. It treats the input like a bag of words. So we lose that inductive bias that recurrence gave us for free. Positional information has to be added back in manually.
Through positional encoding.
Yes. They're just vectors that have the same dimension as the word embeddings 512, and they're literally just added to the token embeddings at the very bottom of the encoder and decoder stacks.
And the authors famously chose these fixed sine and cosine functions instead of just letting the network learn the positional embeddings. What was the thinking behind that?
They use these trigonometric functions that vary based on the position in the sentence and the dimension within the vector. And the key theoretical reason was that this choice makes it incredibly easy for the model to learn about relative positions.
How so?
Because the encoding for any position plus some offset, say pos plus k, can be represented as a simple linear function of the original pos encoding. This means the model doesn't have to learn a new rule for every absolute position. It can generalize relationships based on the distance between tokens.
Let's tie all these pieces back to that revolution in speed and performance. We mentioned the 3.5-day training time. For you, coming from that RNN background, what did that number really represent?
Before this paper, training a top-tier, large-scale model for a task like WMT English to German, it felt like a monumental multi-week commitment, even with good hardware. That 3.5-day figure was genuinely shocking. It immediately lowered the barrier for training massive state-of-the-art models for everyone.
And it was all enabled by that architectural shift, that move from ON sequential operations down to O1.
And the performance numbers proved the risk was worth it.
Hmm.
We mentioned the 28.4 BLEU for English and German. On the bigger English to French task, the transformer hit 41.0 BLEU, beating all previously published single models.
And the kicker.
And they did it at less than a quarter of the training costs of the previous state-of-the-art model. Attention wasn't just good enough to replace recurrence, it was superior.
So we've seen how the transformer just completely sidestepped the reliance on sequential computation. It swapped it for these parallel, constant time attention layers, solved the training speed bottleneck, and just reshaped sequence modeling forever.
And the authors knew what they had. They were already planning, in the paper, to apply it to images and audio. They knew the concept was modality agnostic, which of course directly led to vision transformers and everything that followed.
As we wrap up this deep dive, here's a final thought for you to explore on your own. The authors specifically noted that their fixed sinusoidal positional encodings produced nearly identical results to learned positional embeddings.
Right.
So given that these fixed encodings have the mathematical potential to let the model extrapolate to sequence lengths longer than anything it saw in training, what does that tell you? What does that near-identical performance suggest about the kind of sequence information that language tasks actually need?
Is it really about absolute position? Or is the ability to easily represent relative position through those simple linear functions the most important feature of all? Something for you to mull over.